Okay, so here are the examples that I want you to copy out. I think this one is in the book actually, so you could just do it in there. If your question says find the stationary points as well, just cross that out. This question, I'm just going to do the part where we find the coordinates of the points of inflection and verify the answer by considering points either side. Okay, and this will deal with the proof aspect. You find the point of inflection, but then verify that it is a point of inflection by doing the process I'm setting out. So we've got a cubic function, and it wants us to find the point of inflection. Okay, it doesn't say find the coordinates of the stationary point of inflection. It probably doesn't have a stationary point of inflection. It's talking about the moment. It wants to identify the point where the graph goes from being concave to convex or convex to concave. This happens when the second derivative is 0. Okay, now to do that we need to find the first derivative, which is there. We then differentiate that to find the second derivative, which is there. Now if the point of inflection is at the point where the second derivative is equal to 0, we can solve the second derivative equal to 0 to get x equals 2/3, and there we have the x coordinate of the point of inflection. At x equals 2/3, y equals 47/27, so I just substituted all that into that. I substituted that into all of that, and it's 47/27. So there we are. The point of inflection, i.e. the point where the curve goes from being convex to concave or concave to convex, is this. Now, to prove that, okay, and this is how we might be having to do this, we need to think about points either side of the point of inflection. So if the x coordinate of the point of inflection is 2/3 and that has a second derivative value of 0, if we can show that at either side of that x point that there is a sign change with the second derivative, so it goes from negative to being positive, or positive to negative, that must show that between those two values of x that it must have been 0 at some point. And that's how we do this with a sign change. So by evaluating the second derivative at x equals 0.6 and 0.7, so those are 2 points that are very close to x equals 0.6 recurring, we can hopefully, and I wouldn't write all this out, I'm just doing it for you, we can hopefully show that there is a sign change, which will imply that the curve has gone from concave to convex or from convex to concave. And this shows and proves that there lies a point of inflection in between. So we would go from this to actually working that out. And as you can see, at x equals 0.6, the second derivative is negative. At x equals 0.7, the second derivative is positive. So in between, there must be an x value in between there that gives you a second derivative of 0, and we know that this is enough to say, yeah, it must have been 2/3, 47/27. So you'd finish this off with a statement, therefore the point is a point of inflection. In fact, I would probably have written due to the sign change, so you might want to add that in. Therefore 2/3, 47/27 is a point of inflection due to there being a sign change for the second derivative. That's that. So that's identifying a point of inflection, and now we're going to look at a stationary point of inflection. Very exciting. So, example 2. Find the stationary points for y equals y equals x cubed minus 6x squared add 12x minus 20 and determine their nature. Okay, so that's the sort of terminology you get when you are being asked to find the stationary points, and then see which type of stationary point you have. Now, going back from the previous lesson, we know that we can identify the stationary point when dy by dx equals 0, So we've got 3x squared minus 12x add 12 equals 0. There's only one solution, so we've got x equals 2 as the x coordinate of our stationary point. The corresponding y coordinate is minus 12. So that in itself shows that there is a stationary point at 2 minus 12. Now, to find the nature of the stationary point, to see which kind of stationary point it is, we would go to the second derivative. So the second derivative is 6x take 12, and you know that we would substitute the x value of the stationary point into the second derivative to see which type it is. And so we've got 6 times 2 take 12 is 0. Now, if that was positive or negative, we'd be able to say, yeah, it's a maximum, or yeah, it's a minimum, depending on which it was. Because it's 0, it's inconclusive, and it might be any of the three. And it's up to us to check. And again, we use this idea of trying values of x either side of x equals 2. But we don't do this with the second derivative, because we're not interested in where the curve, we're not interested in whether the curve is convex going to concave. We're interested in what the gradient's doing. If the gradient's positive on one side, then flat, then negative, it would be a maximum like that. So we really need to investigate the gradient. Well, we know the gradient at x equals 2 is 0. What's it doing either side of that point? Now, we take x is 1.9 as the point just to the left of x equals 2. Divided by dx at that point is 0.03. So that means that the gradient is positive at that point just to the left of x being 2. At x equals 2.1, we've got dy by dx equals 0.03. So again, at x equals 2.1, the gradient is positive. And we know that in between, at 2, the gradient is 0. It's stationary. So if we piece all that together, the shape of the graph in that area is going to be, it's got this positive, it's increasing, then it's 0, then it goes to increasing again. And that is an indication of it being a stationary point of inflection. Okay, so there's the difference between a stationary point of inflection and a point of inflection. One is that we've got the gradient is positive, then 0, then positive, or it could be negative, then 0, then negative. The other, as in just a point of inflection, is that we've got concave 0, convex, or vice versa. So that's what I'd like you to copy out today in full, please. Now, could you do that on some paper, make it neat, copy it out like I have, and then make it some sort of insert into your notes, because this is a really important page. It's new on the spec, so there's not tons of questions on it, but I'm going to set you some. But it's going to be really important that you've got a thorough, sort of detailed set of notes on this, because I don't think that the notes in your book do it justice, to be honest. But I think these cover all the different eventualities, and it basically boils down to, are you talking about the curvature of the graph, in which case we were on about convex, concave, and a point of inflection, or are you talking about a stationary point of inflection where the gradient is going from positive to 0 to positive, or negative to 0 to negative? So I'd like you to do that, please, and then I'll set you some work, and then I would have thought there'd be questions on this, but you just give it a good go. All right, cheers. I think we'll do nothing else today. It's a new topic anyway after this, so we can just get onto that on Friday. All right, cheers.